All right, so again, this is the second video for chapter 2. This is about enzymes, and we just had the video talking about anabolism and catabolism and how those are going to form larger molecules, anabolism, or break them down, catabolism, and that's going to help store and then release energy. And so we're going to see how enzymes play a role in that. Now, we said cellular metabolism is all the chemical reactions inside the cell, and that enzymes are what control these reactions. Now, enzymes themselves are proteins, and that's going to be important to remember as we go farther. This is what we refer to as in chemistry, we refer to these as catalysts. Now, again, just like in chemistry, we refer to things on the pH scale from 7 to 14 as bases. In the body, they're referred to as alkaline. These enzymes or catalysts are going to do what we call lower the activation energy. And so this is going to say that this is going to make these reactions happen easier. So enzymes work in small quantities and they're not used up in the chemical reaction. They're just basically something to make it happen, and they can be recycled and reused by the cell. So let's see a little bit about this. Now, each enzyme is specific. That means that there is only one kind of molecule that it can work on, and they are called substrates. So an enzyme, each enzyme has specific substrate. Sometimes there can be two substrates in order to build things up, all right? And we'll see that in just a second. But again, these enzymes are very specific, and they have this three-dimensional structure of the enzyme that is specifically called its conformation. Now, in chapter 2, when we were looking at proteins, we looked at the primary, secondary, tertiary, and quaternary structures, and we were saying primary is looking at the individual amino acids, secondary is kind of looking how these long chains will start bending and twisting, tertiary is looking at the entire protein, and quaternary is looking at how that protein interacts with other proteins. And so the three-dimensional structure, this specific part that's going to bind with the others, that is the active site, and we'll call that the tertiary. When it binds with it, then we're looking at the quaternary structure. Just pointing out that that's why we looked at those when we were talking about proteins. But going back, an enzyme, which in chemistry is called a catalyst, is designed to work on a specific type of molecule. That molecule is called that enzyme's substrate. And it only works on one particular molecule because it has a very specific shape that only fits that one other protein. We call that shape conformation. And in the enzyme, we refer to that conformation shape as the active site. And so what will happen is, if we had molecule A and B, and we're going to see this in a picture, and maybe I should just wait, these are going to sit in a specific spot on this enzyme, and it only fits A and it only fits B. All right, so anyway, we call when those molecules are on there, it's called the enzyme substrate complex. The binding of an enzyme and its substrate changes the shape of the substrate, so the activation energy is lower and the reaction occurs. Now look, all of this stuff is it's very scientific gobbledygook. Right, let me explain what's going on as and we get to a point where I can try to make it more logical here. So the speed of the enzymatic reaction depends on the number of enzymes and substrate molecules available. At the end of the reaction, the enzyme is released and can be used over by the cell. Now again, I'm going to come back to what it's doing and how it lowers the activation rate. So this is a picture showing how the enzyme has this specific active site, this unique conformation shape. And so again, this, as you can see from these arrows, these are reversible reactions. It can go either way, depending on what is needed. And so these are substrate molecules. Looking at it, again, we're not using this way, we're looking at it going towards this. So we're talking about anabolism, smaller molecules here, building larger molecule here, right? And so that is anabolism. So what's going to happen? Imagine having a whole bunch of different molecules. And again, not just this, and I'm going to write, we'll say this is A and this is B, but let's say we have, different ones like C and D and whatever. And so they're all out here and we've got them in this little room and they're able to move around in all kinds of different directions, right? And they're just moving blindly around, and they're hitting the wall and bouncing this way, and occasionally they bump into each other. If I told you that, if I magnified this one and this one and said that that is A and B, and they can't just bump into each other at any angle. They have to bump in perfectly like a puzzle piece. Again, if you've ever put together a jigsaw puzzle, if you took two pieces that actually join together, it actually takes a little force to get them to lock into place. I could put them in a little box and shake it up and they'll bump into each other all the time, but they're not going to hit just perfect to bind to each other or lock into place. And so what ends up happening is when I need this product, my body will produce this enzyme. Its whole job is to get into here. Let me change my little thing. So it gets into here and it's going to go through and it's going to scoop up each of these and it's going to cause them to sit on this little couch called an active site here that is only a couch that only fits the tushies of A and B, and that's it. No other molecule can sit into it. So it forces them to get in, and as they get in there, it actually, the only way they can sit in is to have these little spots next to each other, so it forces them to bind correctly. When this happens, water is going to be released. All right, so since we're creating something larger, again, anabolism, it is done by dehydration synthesis, so removing water, dehydration, synthesis, making. And so we're going to form this molecule, this product, and it's released. This unaltered molecule can then go back and start all over again and continue to make more of these products. And so this is how these enzymes are used. And then when we have enough of this product, we will quit making the enzyme. And now this reaction stops and we can go and about our business and quit dealing with it until we need it. And then our body will produce this enzyme again, and then it starts all over again. If we have a lot of this molecule, and here I'll erase all my chicken scratch on here, but if we have a lot of the molecule on this picture that is called, erase here, that is called the product molecule, let's say that now I've got a bunch of this and I have excess, I don't need anymore. This enzyme can then bind to this, cause it to sit in a way that water will now go in, break that bond, all right, break that bond, and I'll have two substrate products. And again, one side will have a hydrogen and the other side will have this hydroxyl. And so that is catabolism. And so that's how enzymes are used to control reactions. Now, the term activation energy is, again, let's imagine that in our little part here, I have all of these little molecules running all over the place, right? And I want these two up here to meet. Let's say these two right here need to bump together. And again, they have to bump together in just the perfect alignment here. And so if I take and put a flame underneath it and I start increasing the temperature, I've increased the energy, they move faster, so it makes the chance a little more, it's more common, but it's still very rare. It's almost impossible that this is going to happen just by random chance. And so that's why our body produces these enzymes to make it happen. And that's what it means when we talk about reducing the activation energy. Now, different enzymes control different chemical reactions in the sequence of cellular metabolism. These enzymes controlling either anabolic or catabolic sequence reactions must act in a specific order. The sequence of enzyme-controlled reactions for a synthesis and breakdown is called a metabolic pathway. We're going to see that it's not just as simple as A plus B equals AB. There's generally several steps along the way. And so there is one that is called a regulatory enzyme, which is responsible for one of the steps, and by limiting the number of enzyme molecules available. Now this just regulates it, but the real key to it is this one, which is usually the first enzyme needed in this list of different chemical reactions, and it is referred to as the rate limiting enzyme. It is basically, our body will keep all of the little reactants all in a group, and when we need something, we'll create one enzyme, and it will start the ball rolling, so to speak. But once it starts, it will finish. So it's the first step in general that is the one that determines whether the reaction will happen or not. So we call it the rate limiting enzyme. And so this is in this where we've got, these would be the different things we have over here, and then we start the ball rolling. We start this process going with enzyme A. Enzyme A would be considered the rate limiting enzyme, because once we produce this, this will happen, this will happen, this will happen, and this will be the product. And so that rate limiting enzyme is kind of the gatekeeper, so to speak. Now, enzymes generally need help, or sometimes need help in being and their active site. And so we have two things: cofactors and coenzymes. Now, a cofactor is generally what we kind of call an ion. We just talked about them in chapter 2 on pH. When we talk about something dissociated, we call these ions electrolytes. And another way in the dietary world, we call them minerals. Coenzymes are called vitamins, right? And you can kind of remember the Z and the V, both two very uncommon letters. So Z and V are the way that when I was in school, I helped me remember coenzymes were vitamins. But if you can remember, a cofactor is a mineral. I shouldn't have started trying to write this, but if you can remember, a coenzyme is a mineral, and or a cofactor is a mineral, a coenzyme is a vitamin, and a mineral is an electrolyte. You can kind of remember something like Captain Crunch is a very healthy breakfast cereal because it's fortified with vitamins and minerals. And that is a joke. Please don't try to use that on your parents to get more Captain Crunch, but anyway, just trying to come up with things to help you remember that. So cofactors are ions or electrolytes or minerals. Coenzymes are vitamins. And so, for instance, zinc is if you need to take like zinc during cold and flu season, it helps certain enzymes that will be needed in your in immunity. So the same thing is for vitamin C, which vitamin C is needed for a lot of things. But anyway, the big thing is to remember, since enzymes are proteins, they have a specific shape, and that specific shape, if changed, is called being denatured. The things that can change it are heat, pH extremes, I should say, chemicals, electricity, radiation, poisons. But the big one really that we have no control over, we can kind of try to not get out in too much heat. I mean, maybe you can't, but you can try to stay away from certain chemicals. You try to not play with electricity or poisons. But no matter what we do, no matter how clean of a life we live, our body is always wrestling with pH. So pH is a big one. So when we looked at the pH 7.4, which is called physiological pH, the pH of the body, it is really important to keep it in its little set point, because if it gets outside of that, we talked about acidosis and alkalosis, if it gets outside of the normal pH, gets too acidic or too alkaline, it will denature the enzymes, and then our chemical processes, our metabolism will screech to a halt, and we call that death, and that is not a good thing. So that is enzymes. I hope this makes sense, and I hope everybody has a great day.